morning. Good morning for everyone. Okay. Thank you. Well, I'm Luz-Viviana Cobaleda from the University of Antioquia in Medellin, Colombia. My talk today is about enhancing software product lines with machine learning components. So what exactly do I mean by machine learning component, or simply a ML component? It's a special type of software component that encapsulates not only the machine learning model itself, but also the data preprocessing and inference logic and the integration mechanisms that allow it to operate effectively within a larger system. Okay. On one side, the software engineering for artificial intelligence research line explore the challenges of integrating ML components into software systems. On the other side, the software product lines community focuses on how to systematically build and maintain families of software systems with a strong emphasis on the variability management. So our work lies at the intersection of those two lines, exploring how to effectively integrate ML components into software product lines. Well, I would like to talk you through the following 5 points: a motivation, the research questions, the proposed framework with a set of recommendations, a short video about its implementation in VariaMos tool, and finally, the conclusions. Okay. Over the past few years, artificial intelligence has advanced at incredible pace. It has truly transformed the capabilities of modern software systems, enable them to tackle complex problems across a variety of areas, including healthcare, e-commerce, banking, and others. Now, it is common that modern systems include AI components to enable its functionality. We refer to this as AI-based system, or more specifically ML-based systems. They are software systems that rely on at least one ML component to enhance their functionality. So, why not treat this component as black boxes? The ML component don't behave in a strictly deterministic way. Their performance can vary depending on the context, on the data they receive, or even how the model was trained. In other words, the same component might be performed very well in one scenario and poorly in another. Even more, ML components can degrade over time. That's why it is important to establish a proper mechanisms for monitoring and replacement. Therefore, the integration of ML components into software systems introduce unique challenges impacting essential areas such as requirements engineering, architecture, testing, deployment, and maintenance. And also, it's necessary to consider new elements for monitoring and replacement. Now, integrating ML components into a software application is a very challenging task, but the situation becomes even more critical when those components must be integrated not just into a single product, but across an entire family of products, or a software product line. The software product line represents a systematic approach to developing families of related applications within a specific domain through strategic reuse of common assets, and it focuses on systematic variability management. Variability is understood as the capacity of a system to be adapted or configured for specific context. So these challenges don't just persist, they expand and evolve into more complex variability management problems that require new ways of thinking. This raises those fundamental questions. How can an ML component be modeled in the context of software product lines? How can architects effectively integrate ML components into their software product lines? What information about the model is necessary to enable a successful SPL configuration process? Or how can an effective monitoring and replacement process be ensured? Software product lines operationalize this approach through two fundamental processes: a domain engineering, which establishes reusable assets and variability models, and the application engineering, which derives specific products from these shared resources. The configuration process in SPL consists of selecting and combining features from the product line to build a specific product that meets particular requirements. So here the challenges become more significant. For instance, managing a catalog of ML components, each with different performance profiles, and configuring them across multiple products turns into a real variability management challenge. The feature satisfaction moves beyond a simple yes or not. It's not a Boolean satisfaction. This is included or not included. Instead, it becomes necessary to define it in terms of its probabilistic attributes. But the complexity doesn't stop here. ML components are dynamic. They evolve over time. This brings new operational challenges. For example, ensuring freshness of models to prevent performance degradation. In this context, it's necessary to set up continuous monitoring, deciding how much degradation is tolerable, and defining exactly when a model should be retrained or updated. In short, the inclusion of ML components introduces additional layers of variability that traditional modeling techniques are not prepared to handle. We need to define performance metrics not only at the product level, but also at the product line level. We also have to align how different stakeholders understand these metrics and enable a successful SPL configuration process and establish consistent monitoring policies across all products in the line. To address this challenge, we propose the ML Enhanced Software Product Line Framework with a set of recommendations to integrate ML components within the software product line. In our view, machine learning components can simply be treated as simple black boxes within the traditional software product line methods. Instead, they push us to rethink the whole process: how to model the domain, how to describe the components, how we design architectures, and even more, how we configure and derive the final products. We took the software product line framework from Mazo as reference and proposed some suggestions to consider the integration of ML components. The suggestions are organized into 5 interconnected phases: ML-aware domain analysis, adaptive architecture design, the ML-aware domain implementation, and at level of application engineering, we have the dynamic product configuration and the product derivation and validation. Our main contribution is a specification-oriented approach that guides the integration of ML-based functionalities into SPL. The first phase of our proposal is the ML-aware domain analysis. This phase takes place at the domain engineering level. At this point, we identify and specify variability across the product line using formal methods, such as feature models, that define variation points and available alternatives and their constraint relationships. Now, traditional Boolean feature modeling, indicating with whether a feature is present or absent in a specific product of the family, doesn't fit well when we deal with ML components. So instead of relying on static Boolean decisions, we need mechanisms to express and reason about probabilistic and context-sensitive behaviors within our variability models. So that's why we recommend implementing probabilistic future modeling. This involves extending traditional future models with quality performance distribution enable us to capture how the performance of ML components changes across different conditions and to make more informed configuration decisions. The second phase is the adaptive architecture design. Here, the goal is to build a reference architecture that truly reflects the dynamic and context-sensitive nature of ML components. These components evolve over time, depend on external data sources, and their probabilistic behavior can directly affect system reliability and performance. So, our architectural decisions need to support adaptability, traceability, and continuous update to keep the system stable and efficient in the long run. We recommend designing an ML-aware reference architecture that clearly separates the core of SPL framework from the ML model lifecycle. It should also support different deployment strategies, whether that's on the edge, on premises, or in the cloud, depending on each product needs. And of course, it must ensure data privacy, security, and compliance while integrating seamlessly with modern ML engineering practices. In practice, for example, this could mean using microservice-based architectures where ML components are deployed as independent services, well-defined APIs, and adopting containerization technologies. Well, the third phase is the ML-aware domain implementation. At this stage, the focus is on how we actually manage and operationalize the ML components within the product line. This required a structured approach that ensured every ML component is properly documented, versioned, and monitored. Selecting the right ML component is critical here. So the recommendation is to adopt an intelligent component characterization. To integrate each ML component safely and effectively, we need to understand its capacities, limitations, performance, and potential for reuse across different products. To support this, we propose the mandatory use of model cards that are tailored to domain experts responsible for selecting and integrating third-party components. The model card includes information such as model detail, intended use, SPL reusability profile, model usage, operational requirements, performance metrics, and caveats. In this phase, we also need a formal process that can detect when a model performance start to degrade and automatically trigger replacement or retraining procedures. Our recommendation is to implement the systematic ML component monitoring. The monitoring system plays a key role because it helps us deal with the dynamic and non-deterministic nature of ML components by identifying performance degradation and in production and raising alerts when intervention is needed. Since ML components depend so much on data and context, we need robust runtime monitoring mechanisms that continuously observe both model behavior and key business signals. When combined with drift detection and alerting, these mechanisms make our system resilient and self-adaptive, capable of maintaining stable performance even as conditions change. Now, monitoring alone is not enough. Once the monitoring system detects performance degradation, we need a systematic way to respond, a strategy that lets the system adapt automatically. And here, the systematic ML component replacement strategy really plays a key role. It's necessary to set up an automated mechanism that reacts whenever an ML component performance drops below a predefined threshold. These mechanisms should decide whether to retrain the model, replace it with another ML alternative, switch to a traditional software component, or even temporarily disable that functionality to prevent unreliable behavior. Practically speaking, every ML enable component should have its own replacement strategy, a dedicated element that listens for alerts from the monitoring system and executes the action defined in the replacement policy. This approach transforms maintenance into continuous adaptation. Instead of waiting for failures to happen, the system evolves dynamically, keeping stability and quality even as ML components change over time. And finally, we have the challenge of implementing ML component orchestration. Here is essential to make sure that all these components, the models, the monitoring mechanism, and the replacement strategies and triggers actually work together in a coordinated way. Coordinating ML components across multiple products means managing dependencies, activation conditional, and contextual adaptation. When it comes time to replace a component, we need mechanisms to evaluate, decouple, and reintegrate new versions, all with minimal disruption of the system. Continuing with the phases, the next one is the dynamic product configuration, which takes place at the application engineering space. And we recommend to establish multi-objective configuration optimization. Here is necessary to implement mechanisms to balance multiple objectives in ML-based software product line. The last phase is the product derivation and validation. And we recommend to implement validation and testing strategies specifically designed for ML-enhanced products. Validation and testing strategies should incorporate both functional and non-functional assessments, including unit and integration testing, model performance evaluation across diverse data sets, fairness audits, and resources utilizations benchmarking. Now, let's see a short video with the implementation in the VariaMos tool. VariaMos tool is a web-based tool that enables the specification, analysis, and reasoning about software product lines using a multi-language modeling approach. So here we present. Could you confirm the sound?
Not sharing. You should share full.
To implement the recommendation for probabilistic feature modeling that allows reflecting the variability and uncertain behavior of machine learning components within the product line, VariaMos extends the traditional feature model with the new machine learning-based feature element. In the example of the online store product line, we can define the fraud detection feature with an accuracy that ranges between 0.88 and 0.95. This metric is affected by context, decreasing to 0. To implement the recommendation for probabilistic feature modeling that allows reflecting the variability and uncertain behavior of machine learning components within the product line, VariaMos extends the traditional feature.
Great sound. It has sound.
No, there's no sound.
To implement the recommendation for probabilistic feature modeling that allows reflecting the variability and uncertain behavior of machine learning components within the product line, VariaMos extends the traditional feature model with the new machine learning-based feature element. In the example of the online store product line, we can define the fraud detection feature with an accuracy that ranges between 0.88 and 0.95. This metric is affected by context, decreasing to 0.75 for international transactions during the weekend, but reaching 0.98 for transactions coming from suspicious IP addresses. This representation allows us to manage the inherent uncertainty in machine learning-based features, enabling more precise reasoning mechanisms and more informed, adaptive, and reliable product configurations. To implement the
increase.
recommendation related to the characterization of machine learning components, at VariaMos we defined a domain component model. For this purpose, we incorporated a specific element to represent the domain components that integrate machine learning capabilities. For each machine learning component, we integrated the use of model cards in order to systematically document the essential information of each model. For example, in the case of sentiment analysis, we can define a component that uses the Distilbert model, specifying the microservice endpoint for its consumption, the version, the model developer, the type of model, which in this case is text classification, the primary use, the application domains, such as product sales, the performance metrics, and the required computational resources. This same process is replicated to incorporate other machine learning components with similar purposes, such as the Cardic model for sentiment analysis. In the same way, the proposed language allows for the definition of traditional domain components, that is, those that do not incorporate machine learning, thus facilitating the configuration of conventional applications within the product line. To implement the recommendation of systematic monitoring of machine learning components, at VariaMos we defined a dedicated monitoring component, which allows us to establish the strategy, observation, and control for each machine learning component specified in the product line. In the case of the Distilbert sentiment analysis component, this monitoring mechanism allows us to select relevant performance metrics such as precision and recall, define the frequency for evaluating these metrics, for example, a daily evaluation, configure the data collection strategy for evaluation such as continuous real-time log capture, establish a reference for comparing current results like a 7-day moving average, define performance thresholds by specifying minimum and critical values for each metric, configure metrics and thresholds for drift detection, both data and concept drift, identify business impact indicators, for example, the number of misclassified negative reviews, and define intervention strategies such as automatically sending email alerts to the responsible team when an anomaly is detected. This monitoring strategy is applied to each machine learning component defined in the product line, ensuring continuous control over their performance and stability. Additionally, in the VariaMos modeling language, we established an event-based interface that allows the monitoring component to continuously and reactively supervise the behavior of the corresponding machine learning component. The implementation of the recommendation regarding the strategy for replacing machine learning components is realized in VariaMos through the incorporation of the replacement strategy element, which allows for the definition of specific replacement policies for each machine learning component integrated into the product line. For example, consider the Distilbert sentiment analysis component associated with its respective domain component. In this case, it is possible to define a primary alternative, such as the Cardi sentiment analysis component, and a secondary alternative represented by a traditional rule-based component. Likewise, a contingency strategy, the system could be configured to temporarily block requests using a set of predefined rules, thus ensuring controlled behavior in the event of failures. The replacement strategy remains subscribed to the events generated by the monitoring system so that the replacement of the degraded component is executed automatically as soon as an anomaly in its performance is detected.
Presentation here. Okay. Well, finally, as a conclusion, our main contribution is a specification-oriented approach that guides the integration of ML-based functionalities into software product lines. This approach addresses key aspects, including variability management, probabilistic feature modeling, ML component characterization, systematic ML component monitoring, systematic component replacement strategy, and derivation products with ML components. This strategy enables more systematic reuse, customization, and traceability of ML components across product configurations in the software product line context. As a future work involves evaluating the proposed strategy in the real-world industrial domains, extending the capabilities of the VariaMos tool, and exploring its applicability to AI components beyond ML. Thank you very much.